We're going to take a look at how to simplify radicals. We're going to start with just a simple square root problem. So we have negative 2 times the square root of 54 x cubed y squared. So you have a couple different options. You can think about what your perfect squares are, and your perfect squares would be things like 1, 4, 9, 16, 25, 6 squared is 36, 49, 8 times 8 is 64, 81, 100, 121, 144, and so on. So those are our perfect squares. So we can think about which of these are factors of 54. You could also use prime factorization, so I'll show you both ways. So we have negative 2 times, and we're going to break this apart. So 54 is 9 and 6, so we have 6 times 9. And then x cubed, well, that's the same as x squared and x, and then we have y squared. I separated these two because I can take the square root of x squared. X can't take the square root of x cubed. So now really what I have is negative 2 times the square root of 6, the square root of 9, the square root of x squared, the square root of x, and the square root of y squared. Well, square root of 9 gives us 3, so square root of x squared gives us x, square root of y squared gives us y. And then we have these leftovers, square root of 6 and the square root of x. So 3 times negative 2 would give us negative 6. We have x, y, and then we have the square root of 6x. Now, since this is an even root, square root, or the fourth root, or the sixth root, coming out of the square root is not going to be, these two numbers have to be positive coming out of that square root to work. So we're going to put absolute value marks on either side of our x and our y to force them to be positive. If you're taking a cubed root of negative 8 is negative 2, so we don't need those absolute value marks. Another way to do this problem, and actually we're gonna do the other method on the next example that we're going to work here. Let's do let's try something like this one. This is number 10. We have negative 8 times the cubed root of 84 n squared. So let's think about our perfect cubes. Perfect cubes, 1 cubed is 1, 2 cubed is 8, 3 cubed would be 27, 4 cubed would be 64, and we can go on from there. So if we look at 84, we're going to do the prime factorization method here. You could have done that in the first one. The cubed root of 8, well, 84, let's see, 84 breaks into 2 and, let's say, 41, 42. 2 times 2 is 4, 2 times 8, or 4 is 8, 2 and 42. 42 breaks into 2 and 21. And then we have 2, 2, and 21 breaks into 3 and 7. So we can see that none of these, this index is a 3. It's a cubed root. It means that we need 3 of them before we can, before they can come out, or you could actually evaluate, like square root of 9 is 3 times 3. So the square root of 9 is 3. This one, though, we can't really do much with it because I didn't choose a good problem. So there's not really anything there, n and n. That doesn't work out for us either, so it's just reduced as it is. Let's try another one that looks like that. Let's do, I'm trying to find a good one. Let's do this one. We have 8, this is number 11. We have 8 cubed roots of negative 24k to the 8th. Now, we have a negative, but it's a cubed root, so that's okay. So I'm just going to separate that out. I'm just going to put a negative 1. And now 24 breaks into 4 and 6. That breaks into 2 and 2. And 6 breaks into 2 and 3. So I've got 2, 2, 2, and a 3. So when I'm evaluating that, I need sets of 3 of them. So 2 times 2 times 2 is 8. The cubed root of 8 is 2. The cubed root of negative 1, well, negative 1 times negative 1 times negative 1 equals negative 1. So the cubed root of negative 1 is negative 1. So really I have negative 16 cubed roots of 3. So that's how you simplify